Now that we've solved a simple second-order differential equation, we should formalize the process. So we'll start with some definitions. A general second-order linear ordinary differential equation is given by y double prime plus p of t times y prime plus q of t times y is equal to some function, we'll call it g of t. So what makes this a linear ordinary differential equation? Well, we can say that the operator, which is what is done to y on the left side of the equation, so the operator L, which is d squared dt squared, plus p of t times d dt plus q of t, that operator is linear. So what is being done to the left-hand side of the equation is a linear operation. And what do I mean by linear? I mean that L done to the sum of two solutions, y1 plus y2, is equal to y1 plus ly2. And that L done to a constant times y1 is equal to that constant times L done to y1. So L is a linear transformation in the sense of a linear transformation in linear algebra. We need to verify these two properties, but these can be easily verified because the derivative is itself a linear transformation, and so is the second derivative. And multiplication by a function p of t or q of t is also a linear transformation. I leave it to you to verify that these two properties are true on your own. Okay, so a second order linear differential equation could be homogeneous if g of t is equal to 0 for all t, so that the right-hand side of this linear differential equation is always 0. And then it's non-homogeneous if g of t is not equal to 0 for some t. And then we want to talk about existence and uniqueness. So I'm not going to get into the general existence and uniqueness theorems for second order differential equations, but I can tell you about when solutions exist if I'm dealing with a second order linear differential equation. So I will just state without proof for now that solutions exist where the functions p of t, q of t, and g of t are continuous. So as long as those functions are continuous, then we can say that a solution exists. Okay, so let's move on to understanding the homogeneous problem. So the homogeneous problem is when Ly is equal to 0. We've already seen an example of the homogeneous problem. We saw y double prime plus or minus omega squared y is equal to 0. And because we essentially have a linear operation done to y equals 0, we call that the homogeneous problem. So let's look at a fact. The set of solutions to a second order linear homogeneous differential equations actually is a vector space. It's a vector space of dimension 2. In fact, it's not just any vector space, but it is the kernel of the linear transformation y, or the null space associated with that linear transformation L. Okay, so essentially what we're going to be doing is trying to find the null space of this linear transformation. So why is it that that is a vector space? Okay, well, we're going to let y1 and y2 be solutions to the linear differential equation. So in other words, we're going to say that L done to y1 is equal to 0 and L done to y2 is equal to 0. And then what I want to do is I want to show that L y equals 0, that those solutions form a subspace. Okay, so we should mention that this is a subspace of twice differentiable functions. So you probably showed in a linear algebra class that twice differentiable functions form a vector space, or that just functions in general can form a vector space. Okay, so if we have two solutions, then if we do L done to the sum of those two solutions, then that's actually L done to y1 plus L done to y2, but each one of those is 0. And that shows that y1 plus y2 is in the vector space. But we can also do L done to C y1, and that's actually C L done to y1. And of course, L done to y1 is 0, so that's C times 0, which is 0. And so a constant multiple of a solution is also a solution and is in that vector space. So since we've shown these two properties, okay, that we're closed under addition and scalar multiplication, since we've shown both of those properties, then we can say the solutions form a subspace, and it's a subspace of the twice differentiable functions. Okay, what is this subspace? It's the kernel of L, or you can think about it as being the null space of that linear transformation. Okay, so solving the homogeneous problem is really about finding a basis for the vector space. So what we're looking for is we're looking for a fundamental set of solutions. And that fundamental set of solutions is going to form a basis for our vector space. So essentially, we're looking for linear independent functions that span our space. And that way, the general solution is a linear combination of the basis functions. So in other words, it's a linear combination of y1 and y2. And we saw before with our previous problem, okay, we had an example, right, that y double prime plus omega squared y is equal to 0. And so our general solution was that y equals c1 cosine omega t plus c2 sine omega t. So I am inferring that cosine and sine are the fundamental set of solutions to that problem. In other words, that they form a basis for our vector space. Well, that requires me to know that the cosine and sine functions are linearly independent and that they span the space. So let's talk about how we would show that two functions are linearly independent. Okay, so another fact that we will use is that two functions are linearly independent using the definition if c1 times y1 plus c2 times y2 equals 0, that implies that c1 and c2 are identically 0. So the only solution to that equation, if it's that c1 and c2 are 0, then I have two linearly independent vectors. Okay, so in this case, we're going to have two functions. And so that means that we only have one equation. We have one equation that we're looking at. It's that c1y1 plus c2y2 is equal to 0. But we have two unknowns. We have c1 and c2. So how could we possibly show, with just one equation and two unknowns, okay, that there's a unique solution and that it has to be the trivial solution, that c1 and c2 is 0? Okay, well, we would take a derivative. If we take a derivative of our equation, then we're going to get a second equation. Okay, that equation would be that c1y1 prime plus c2y2 prime is equal to 0. And so now I have two equations and two unknowns. And so now I can show when c1 and c2 must both be 0. So we're going to write this system as a system of equations. And that system is the matrix y1, y2, y1 prime, y2 prime, times the vector c1, c2 is equal to 0. Okay, if we had two vectors, by the way, kind of as a side note, when we had two vectors, so let's say we did c1 v1 plus c2 v2 is equal to 0, then what we would have done is formed a matrix v1 v2, whose columns are the two vectors v1 and v2. We would have multiplied that matrix times the vectors c1 c2 and set it equal to 0, and then we would have solved for c1 and c2 to show that those two vectors were linearly independent. Okay, so we're doing the same thing, but now our matrix is not formed by the columns of y1 and y2, but actually y1 and y1 prime for the first column and y2 and y2 prime for the second column. Now, this particular system has only one solution, and that solution is only the trivial solution if my matrix is invertible. But what's a nice easy way to show that a matrix is invertible? Well, if the determinant of that matrix, formed by y1, y2, y1 prime, y2 prime, if the determinant of that matrix is not equal to 0, then then the matrix itself is invertible and there's only one solution, the trivial solution. Okay, so showing that two functions are linearly independent comes down to taking the determinant of this matrix and showing that it's not equal to 0. Well, the determinant of that matrix has a name. It's called the Wronskian. Okay, and so the Wronskian can be used to determine whether two solutions to the differential equation are forming the fundamental set of solutions if they are linearly independent. Okay, so if they're linearly independent, then we can show that that determinant is not equal to 0. So we're going to say that W of the two functions, okay, is the Wronskian. Now, that really only shows independence, okay? But the second thing that we really need is that the two solutions need to span the entire space. Now, the space has a dimension of 2, okay? So if I find two linearly independent functions, then I can say that they span that they form a basis and that they span that vector space, okay? But I want to know under what circumstances am I going to be able to show that those two solutions span the entire space, okay? And so if you go back to the previous example that we did, you notice that we had a second order differential equation and it had two initial conditions. So in fact, to make sure that our two solutions span the space, we're going to need two initial conditions. Okay, so why is that the case? Let's suppose y1 and y2 are linearly independent solutions of our equation. We'll call it Ly equals 0. Okay, and then what we're going to do is we're going to specify 2 points. Y of t0 equal to y0 and y prime of t0 equal to v0. Okay, so we have an initial position and an initial velocity. Then we have that c1 y1 of t0 plus c2 y2 of t0 is equal to y0. Okay, so that's just plugging in t0 to our solution and saying it must equal the initial position y0. But we can also plug t0 into our derivative, so that's c1 y1 prime of t0 plus c2 y2 prime of t0, and that would have to equal v0. Well, I'm going to write this in matrix form. Okay, I'm going to write this as y1 of t0 and y2 of t0, and then y1 prime of t0 and y2 prime of t0 times c1 and c2 is equal to y0 and v0. Okay, so this linear system that I've written has a unique solution where I can specify c1 and c2 if the determinant of that matrix is not equal to 0. Well, since we're going to start with y1 and y2 being linearly independent, then that determinant that I'm looking at is actually the Wronskian of the two functions. And I've already shown that those are not 0 if I'm starting with linearly independent functions. So that means that this system has a unique solution. So if I'm given a y0 and a v0, an initial position and velocity, I can solve for c1 and c2. Okay, so given initial position velocity, we can solve for c1 and c2. And that means that we can solve this initial value problem. So let's look at an example. Okay. So I want to solve the homogeneous differential equation y double prime plus 4 times y is equal to 0. So we actually solved this one before, right? It's in the form y double prime plus omega squared y is equal to 0. So I know that the fundamental set of solutions is going to be cosine 2t and sine 2t. That's because we solved this problem already. So I suggest, okay, instead of going through all of the process that we went through in the last video for learning how to solve this equation here, that instead that you learn that the solution to this this particular second order differential equation is just cosine omega t and sine omega t. That those are the two solutions that form this fundamental set of solutions. Okay, so why do I know that they're linearly independent? Well, I would have to take the Wronskian of both. So I'm going to take the Wronskian of cosine 2t and sine 2t. So that's the determinant of the matrix that has a cosine 2t and a sine 2t. And then the derivative of cosine 2t is negative 2 sine 2t. And the derivative of sine 2t is 2 cosine 2t. Now, the determinant of that matrix is going to be 2 cosine squared of 2t minus a negative 2, I'm going to put it as a negative 2 sine squared 2t. So I have 2 cosine squared 2t, essentially plus 2 sine squared 2t. And so that gives me 2. And so the Wronskian is 2, which is certainly not 0, which shows me that the two functions are linearly independent. Okay, so something I didn't mention before, but the Wronskian does not have to equal some constant that's not equal to 0. It just has to not equal 0 for some t. Okay, it doesn't have to not equal 0 for all times. It just has to not equal 0 for some times. So I'm actually going to go back and update this theorem for a second. Okay, and I'm going to mention that that this Wronskian is not equal to 0 for some time. It only has to be 1. It doesn't have to be all t. Okay, so not necessarily all t. Okay, but it just so happens in this case that the Wronskian was not 0 for all time. Okay, so that tells me my fundamental set of solutions is cosine 2t and sine 2t. So I get that y is equal to c1 cosine of 2t plus c2 sine of 2t. So I have found a general solution to the differential equation. But now I'm going to add to this differential equation. I'm going to add 2 initial conditions. I'm going to start with y of 0 being 1 and y prime of 0 being negative 2. So I can just plug those in. Y of 0 is equal to c1 cosine of 0 plus c2 sine of 0, and that's supposed to equal 1. So sine of 0 is 0 and cosine of 0 is 1. Okay, so that tells me that c1 is equal to 1. And now I'm going to take the derivative. Y prime of 0 is equal to negative c1 sine of 2 times 0 times 2. So there's a negative 2c1 sine of 2 times 0 plus 2c2 cosine of 2 times 0. Okay, and then sine of 2 times 0 is 0, and cosine of 2 times 0 is 1. So that actually tells me that y prime of 0 is equal to 2c2, and we're going to make that equal to negative 2. So that tells me that c2 is equal to negative 1. Now, just so you notice, I did kind of cheat a little bit. I both found the derivative and plugged in 0 in one step, and I don't recommend that. You should probably find the derivative first and then separately plug in 0. But in this case, y of t is equal to cosine of 2t minus sine of 2t. And that is the solution to this initial value problem. And you might say to yourself, well, now I'd like to plot that solution. And of course, you can use technology to plot that solution. But maybe we could manipulate the solution of cosine 2t minus sine 2t so that we can write it as basically either one cosine or one sine, where it's easy for me to see what the amplitude is, what the phase is, and what the period is. And that's what we'll do in the next video.